So yesterday we were halfway the proof of this theorem, which is orthogonality relations. And so the idea is that we first consider function from G to C, and the characters we're going to discuss are exactly functions from G to C. And on them, we put this inner product, which is the standard inner product for vectors. I mean, the sum, if you have a vectors whose components are AI and BI, this is the standard inner product with the conjugate here. And you see such a function as given by its string of values. So instead of having indices going from 1 to n, you have indices over the group, G1, Gn, say, the group is order n. And we put this factor 1 over order of G in front, so an averaging factor for a reason that will become apparent once we review the second statement in the theorem. So what we have proved yesterday is that if you take the characters to non-isomorphic irreducible representations, then they are orthogonal. The inner product of the two of them is 0, okay? And this depends on the results we already know about the components of the underlying representations. We'll review that in a second. And then we were left with proving, 3 is just the sum of the two previous, the union of the two previous results, that if you have a single irreducible representation, then the inner product of the representation with itself is 1, okay? And how do you do that? Well, let's recall, first of all, what a character is. You consider representation from G to GLV. And its character is nothing else than the trace of this matrix, say, okay, if you see GLV, the elements as matrices. So let's see what the inner product we have to compute looks like. So it's an average over G of the conjugates of the value of chi on G times chi of G. Well, okay, so if we use so if chi of G is the trace of rho of G, we use, as usual, the notation rho to ij to indicate the ij component of the matrix. So this being the trace, this will be the sum. Okay, say if the dimension of V is n, okay, then this character will be the sum of rho I of G conjugate, okay, I from 1 to n. This is the sum, except that we have a conjugate here, right? Is the sum of the elements on the diagonal, so when the two indices are the same. And of course, we get this is the same for this. We have to use clearly a different index. Okay. And now this becomes 1 over G, over order of G. So let's say sum over ij going from 1 to n, and then sum G over G of rho II of G conjugate, rho JJ G, okay? And now our results on these components tells us that if we do the same with any two representation, we always get 0, unless the representation is the same on the two sides, and this is exactly the case we are in. And the indices are exactly the same. So this can only be non-zero when the indices are the same. All other terms, no, sorry, this is an II. The indices have to be the same. Okay? And then when this happens, when the indices are the same, this sum, okay, equals is a constant, is over order of G over n. Okay, so we had proved that this has to be a scalar, and the scalar is exactly this. We are summing this from 1 to for I 1 to n, and this has become a constant now. So you sum n times the same constant, and as you see, these two simplify, and we are left with 1 as we wanted. Okay. So you see that this factor here, 1 over order of g in front, is needed to obtain that they have norm, say, inner product 1 with themselves. And then, of course, point 3 is immediate because we are stating that the characters of the reducible representations are orthonormal, okay, with respect to the inner product, to this inner product. I mean, the characters of two non-isomorphic representation are orthogonal. And if you take a character of a single irreducible representation, then it has inner product with itself equal to 1. Okay? But this fact has an important consequence because we obtain this very important fact that the character of representation determines let's say the representation itself up to isomorphism. So isomorphism in the case of representation really means up to a change of basis. So it's the same representation except that we are changing the basis. So recall the concept of isomorphism, a linear map which commutes with the representation. And this is important because this really explains why the characters are at least economical. Because as I said, declaring a representation, no, let's do it in black. Because declaring a representation from G to GLV requires giving dimension of V squared numbers, complex numbers for every element of G. Whereas if you declare a character, it's just 1, okay? 1 value for each element of G. It's extremely economical. You save a lot of, say, space. Oh, by the way, we will give a proof that is, say, in concept. But one of the seminars is about reconstructing a representation from a character. So this just tells you that you will find exactly one representation which affords the character. So exactly one representation such that this holds, okay, up to isomorphism. I mean, given a character chi, then you obtain exactly one up to isomorphism representation rho. One of the seminars is about how to construct explicitly the rho from the chi. So there is how to get from one function, from G to C, to dim V square functions. Okay, how do you get, okay, yes, how can you obtain several functions from one? Okay, the proof is really, no, proof, not that dim. The proof is rather immediate, but it's important so that we can recall a few important facts. So recall that as a consequence of Maschke's theorem, we have Maschke's theorem as an important consequence that every representation is a direct sum of irreducible ones. Which means that if you have a representation rho, like here, then you can write rho of G, say a matrix, as a blockwise matrix, okay? Where, so you have only non-zero entries on blocks on the diagonal, like rho 1G, rho 2G, and so on, rho whatever, K of G, okay? and zeros elsewhere, okay, where each row I, so row will be a function from G to GLV, some V. The row I will be a morpheme, sorry, to some VI, where the direct V is the direct sum of this VI, okay? And these are irreducible, and the row I are irreducible representations. Okay, and I'm going to write something that's slightly different now. And so we have used the notation that rho is the direct sum of row 1, row 2, row k, meaning exactly this, okay? It's nothing else that, well, that the matrix which is blockwise diagonal, okay? So what we have here is that the V1 is a rho G invariant subspace, and rho 1 of G represents the restriction of rho to V1. V2 is rho G invariant, and rho 2 of G is the restriction of rho G to rho 2 of G, and so on. And it's a direct sum, okay? But we go one step further, and if rho equals rho 1, so we group together isomorphic representations. Okay, so this is slightly different notation with respect to the previous one. Let's see, I have just T. Okay, so this means that you split each row of G as a blockwise matrix, and the diagonal you have row 1 of G, row 1 of G, and so on, say n1 times, and then row 2 of G, row 2 of G, n2 times, okay, and this empty times, with row I, row J not isomorphic for I different from G. So you group together all representation are isomorphic. And of course, I'm writing exactly the same representation because if these are isomorphic, it's just a matter of changing bases, and then they are as equal. Because two isomorphic representations are nothing else than the same representation with respect to a different basis. Okay, and we write compactly something like this. Okay. So this means that this is a direct sum of n1 copies of row 1 and so on, okay? Then you compute the trace. And of course, when you compute the trace of such a matrix, you get a trace of this plus the trace of this plus the trace of this. There is, if you apply the trace, okay, since this is a blockwise matrix, the trace of this direct sum, so the character of G, which is the trace of row of G, will be nothing else that n1, the characters of sorry, not n1, k1 of G plus n2 k2 of G plus and so on, plus nt kt of G, where of course ki of G will be the trace of row I of G. Now, well, let's write it on a single line. Okay, just taken this. Okay, so or if you prefer, I can write this as a sum of functions. Okay. Yes. Well, okay. Fine. So now the point is let chi be just a second. Yes. Okay. Now let us compute for one of the I this scalar product. Okay. since this inner product, I will say scalar sometimes, this product is of course linear in this component and semi-linear in the other. I mean, in the other you get the complex number coming out, but the complex conjugate coming out. So I mean, since chi is the sum of this, you'll obtain that this will be the sum for, say, j from 1 to t, chi I, chi j, okay? Because chi, the character of rho, is the sum of n1, sorry, with ni in front, okay? Or nj in front, okay? Because chi is the sum of n1 times chi1 and 2 times k2 and so on. But the result we have just proved says that this is always 0. This is 0 unless j is equal to 1. And so the only term that survives is n I, chi I, and this is 1. So this tells you have a character, okay, of a certain representation. And you know, I mean, and you know by Maschke that the representation will be a direct sum of certain copies of irreducible representations. You don't know the ni. But this tells you, okay, fine, you have this character, you compute the inner product with the chi I, and you find exactly ni. And this you can do for all I. So this means you know what n1 is, what n2 is. I mean, you just find them by taking this inner product. And now you know what rho is, because rho will be the direct sum of this n1 times of this representation, plus n2 times of this representation, plus nt of this representation. So you know the ni, and this determines rho up to isomorphism. Okay? So since a representation is determined by these numbers, and you can obtain these numbers just by this calculating this inner product, a character is enough to tell you what the representation is. Okay? And as I said, this is important. In particular, this definition now makes sense. A character is said to be irreducible if the representation that affords it is irreducible. And of course, the representation that afforded is a representation rho such that it holds, okay? The character is a trace of this representation. And the point is because the type of rho is determined up to isomorphism. So if it's the character of a reducible representation, all other representation that gives chi, therefore chi, have to be irreducible, okay? Good. So we have found that characters are an economical way of describing representation. But now we may wonder, given a group G, remember this is always a finite group, how many irreducible pairwise not isomorphic, non-isomorphic representations or characters G has. And here you have to say non-isomorphic, but the point of characters, in other words, we are wondering how many reducible characters there are. Let's say distinct, but this is usually, of course, irreducible characters are there. Does G have? Okay. Yes, here, does G have is better. How many does G have? Because two representation can be isomorphic or non-isomorphic, but characters are equal or distinct. And as we saw yesterday, because of the properties of the trace, if two representations let's recall this. What does it mean for two representation, rho one, rho two isomorphic? I'm sure I did it yesterday, but let's repeat it. Means there exists F in GL V, well, okay, no, F. As usual, F, well, I'll never remember it. F from V1 to an isomorphism, bijective, a linear invertible. Such that F commutes with the rho I, so I take rho 1 of G, which is of course on V1, and then I apply F, and I end up in V2, and this will be the same as this, okay? So this is from V1 to V1 to V2, and this is from V1 to V2 to V2, so these two are the same, which means that rho 2 of G is F inverse times rho 1 of G, F. And if you take the trace, because the trace has the property that you can exchange factors inside the trace, this will be exactly the trace of rho 2 of G. This is not, yes, that's, just a second. It's rho 1 of G. Okay, so two isomorphic representation have the same, exactly the same character because it's a trace. So to say non-isomorphic representations means distinct characters, and then of course you don't normally say distinct. Okay, so how many of these there are, and when can you, and where can you find? Can you find them? Is there a place where all these irreducible representations live? And yes, there is a place, and this is the regular representation. So recall what the regular representation is. And yes, we'll introduce a way of writing the regular representation, which is particularly important. So let rho from G to GL, and I'll tell you in a second what I'll put here, be the right regular representation. So the idea is that the right regular representation begins its life as a permutation representation. So to G, you associate to a certain permutation of G itself. And then you construct a vector space which has the element of G as a basis, and you simply let an element of G act on the basis element, and then you continue by, and then you extend by linearity. But then, I mean, this is probably the first time we're doing this. I can put this, the group algebra here, because the group algebra, after all, is a vector space which has the elements of G as a basis. Remember that we constructed a group algebra similar to the polynomials that functions from G to C, and then we found that there's a way to identify a certain delta function, the delta function of an element G of G with G itself. So the element of C of G are linear combinations of the element of G in a unique way. This is a basis, okay? And then what's the right regular representation? It's the representation that takes an element, say, H, to the map that takes an element of the group algebra to what you obtain when you multiply this by G. Okay, let's put parentheses here because this is again an element of the group algebra, a linear combination of these elements of G. I mean, of course, you could rewrite this, write this as K and sum over K, and okay. Yes, it's absolutely the same. Okay. Okay. So an element of G. The right regular representation is the morphism from G to the linear group of this vector space. So this is an algebra, okay? But you regard it for a moment just as a vector space, which has the element of G as a basis, and an element H is sent to a map that multiplies one of the elements by H. There will be more about this in a second. Good. So on the basis, well, of course, this is a vector space which has the element of G of the basis. And of course, you can describe this linear map. This is clearly a linear map. Okay, because it's multiplication in a ring, in an algebra. And in a ring, of course, you have the distributive properties, which gives you the fact that it's a linear map. And so if you look at this on a basis, well, on the basis provided by the G, the H is sent to, well, we are going back to the permutation representation, sends G to GH, okay? So you think of the elements of G as the basis of this vector space, and on this basis, H acts by right multiplication. I mean, it's the right regular representation after all. And so the point is that, this will be a matrix, okay? And we want to compute the character, okay? So psi of G will be the trace of rho of G, okay? And so the trace, what's the trace? The trace is the sum of the elements on the diagonal, okay? So when do we have an element on the diagonal here? So this is the basis, okay? And we ask ourselves, when is it that, that this G goes to a multiple of the same element? But really, there are no multiples here. This G is sent to another basis element. So, and we know that G equals GH, that is, we have an element, we have a 1 on the diagonal, only when H equals 1. Of course, because you multiply on the left by G inverse. Just to make this clear, let's consider a very simple example. So for instance, let's consider simply the group of order 2, okay? Okay, so a C of G as basis 1G. We've already done this as an example. And so if you have, well, of course, rho of 1, what will this be? Rho of 1 is the matrix that sends 1 to 1 times 1 and G to G times 1, okay? So you see, this is, of course, the identity, okay? The identity, because you write the elements of the basis here on the left and on top, and then you're seeing here that 1 is sent to 1 and G is sent to G. But what happens if you consider rho of G? Again, this is the map, the linear map that, I mean, just look at what happens on a basis, because this is what we need to write down a matrix, okay? Of course, when I write nothing, it's a 0. So I multiply this by G and I get G. I multiply this by G and I get 1, because this is of order 2. So what does it mean? That the matrix will be, okay, 1 is sent in G, this is 1 here, and G is sent to 1, okay? So the trace of rho 1 will be 2, because this is a two-dimensional representation, and the trace of rho of G will be 0, of course, because there's nothing on the diagonal. But this is a general fact, because you can have something on the diagonal that is, you can have G going to G only when H is 1, okay? Otherwise, multiplying by an element different from 1 changes this from G to another element, and then it won't be in the diagonal. It will send G to something GH, which is different from G, if H is different from 1. Okay? So what we found that in general, so this was just for the group of order 2 to understand on a concrete example. In general, the trace of rho of G is, say, the dimension of V, is the order of G if G is 1. Well, let's write it H, because I was using the letter H. If H is 1. And the trace of rho H will be 0 if H is different from 1. Because if you have H equals 1, well, of course, this will send each element on itself, so we'll have all ones on the diagonal. But if the elements is different from 1, this is different from 1, then you have nothing on the diagonal, because multiplying by an element different from 1 changes the element of the group, okay? Because you can simplify in a group. Once more, this GH can be equal to a G only when H is 1. And then this is true for all Gs, okay? And this is actually the character, okay? So the for the character of the right regular representation, we will have, of course, this trace here will be the order of G, because this vector space on which you are acting has dimension exactly the order of G, because it, as a basis, it has the element of G. So we will have, I'll repeat what I write here, psi of 1 equals the order of G, and psi of, say, H equals 0 for H different from 1. So it's a very simple character. It has all of its values when you take the order of G, and all the rest is 0. But then you wonder, let chi be an irreducible character. Okay? And let's compute. Okay, fine, before doing this. So suppose that the right regular representation is, as we wrote earlier, N1 rho 1 plus N2 rho T with rho I irreducible. So Maschke's theorem tells us that any representation splits as a direct sum of irreducible one. So we are wondering, irreducible, say, pairwise non-isomorphic, okay? Okay, so we wondered what the ni are. And of course, we can go to the character. Well, let's write direct sum, but it means exactly the same. So where chi I mean, psi or psi, well, is the trace of the character associated to the right regular representation, and chi I is the character associated to the rho I. Okay, so we wonder what are the ni. So take any irreducible character. Okay. Yes, and well, let's say chi I be an irreducible character, and we compute psi chi. Okay, so chi I. So we know this is ni. Okay, we saw it earlier. Okay, that if you multiply by a certain character, this gives you the ni. Okay, except that we have to determine the ni. We saw earlier that this just a couple of pages ago that this is the number of times the representation affording chi I occurs in the decomposition of rho as the direct sum of irreducible representation. But what's this? Well, so this is the 1 over order of G, sum G in G of what? This is the standard inner product. So we'll have a psi of G conjugate times chi I of G. Okay, but this sum is actually very, very poor, because the values of psi are always 0 except for G equal 1. Okay, so there is only one term that is non-zero, because since it is a sum of products, Every time psi of G is 0, you get nothing. So you get exactly one term, okay, which is this. Okay, let's see, for G equals 1. And then, of course, here you have the same G. Well, of course, these two conveniently cancel out, and you get chi I of 1. So you see that what you've seen is that in the right regular representation, a character, an irreducible character chi I, occurs exactly ni times, where ni is the value of chi I at 1. We probably noticed already last time, but let me repeat it, if rho I from G to GLVI, I'm going to repeat what I just stated, is a representation. Okay, and chi I of G is the associated character. So what is chi I of 1? Is the trace of rho I of 1, but the rho I are morphisms, so this is the identity matrix. Okay, and so the trace of the identity matrix is exactly equal to the dimension of VI, because the identity matrix is the matrix whose dimension is the dimension of the vector. So this is exactly the dimension of VI. Okay, and this is called the degree of the character. Yes, it's a dimension, so it could be called a dimension, but it's customary to call it the degree of a character. Okay, so what we have found the first part of the following theorem. Every irreducible representation with the character chi occurs chi 1 times in the decomposition of the right regular representation as a sum of as a direct sum of irreducible representations. So this is very important because it tells you that my question was, where can you find all the reducible representation? Every reducible representation can be found in the decomposition of the right regular representation. Not only, but you can find it several times, exactly how many times as the dimension of the vector space on which you have the representation. Okay, so okay, fine. Because let's review it's the power of characters that's showing up for the first time, because you write the right regular representation as a direct sum of irreducible representations, and you don't know which representation occur and how many times, but we take any irreducible character, okay, any irreducible character, you find that this occurs in the character of the representation exactly ni times, exactly, sorry, chi I of 1 times, which is of course different from 0, because this is a dimension, okay, as we saw, this is the dimension of VI. So of course it's different from 0. So it means that within the right regular representation, you find all irreducible representations. And the representation rho I occurs here exactly as many times as the dimension of the underlying vector space. Okay, so this the right regular representation is a nice place to find, at least in principle, all irreducible representation of a group. Okay? No, sorry, forward. So every irreducible representation with character chi occurs chi 1 times in the decomposition of the right regular representation as direct sum of irreducible representation. And remember, chi of 1 is the dimension of the vector space. underlying vector space. So it's the trace of the identity matrix, okay, which has, of course, as many ones as the dimension of the vector space. So this is part 2 of this theorem. And, well, an immediate consequence, because you see I have this equality here, and then I've written this equality in this form in the characters, but the meaning is the same. So the meaning is the same. Well, let's write it and then I'll make it precise. So if psi, as a consequence, is the character of the regular representation, then psi is the direct sum, no, sorry, no, chi. I write chi on the left, because I want to add something here, chi1, chi, okay? So this really means, okay, fine, where chi ranges over IRG, where IRG, this is also standard notation, is the set of the irreducible characters. Of G. Okay, and this is exactly what I wrote this in this form. What I wrote in this form. Okay, and this really means simply that for G in G, for all G in G, we have that the value of the right regular representation on G is the sum over all irreducible characters of chi1, chi G. Okay. I mean, this written like here without the G really implies that you have this equality in the values. It's just a simple way of writing it without the argument. Okay. And there's a third consequence, which is, as you see, apparently harmless, but it will have a great impact. So what happens when you compute this on one? Okay. So what happens when you compute? So let's do it on the next page, and then I'll be back and state this. So I just found that so this is the character of the right regular representation. So this is short for right regular representation, is the sum where chi ranges over all irreducible characters, or of so it's let's compose it. It's the sum of all these irreducible characters, but each irreducible character appears chi1 times. So remember, this is the value of the character in 1, which means it's the dimension of the align vector space. But then this means, as we saw here, that you can evaluate in each G on G. There's a particular value which is of interest if you do psi of 1. And remember, this is the order of G, okay? So if you look at the character of the right regular representation, psi of 1 would be the trace of the identity matrix. And since you're acting on C of G, which has dimension the order of G, you get the order of G. So this means that you'll have this. Okay, you had already a chi1 here. Now you have the chi which you are evaluating in 1, and so you have simply obtained that this is chi ranges over the reducible characters squares. Okay, and this is exactly the content of the third point, which I'm going to write. Then I'm going back here. So the order of G is equal to the sum where chi ranges over the reducible characters of G of chi1 squared, okay? In other words, this is the sum over, say, I of the dimension of the I squared, okay? Where the rho I from G to GLBI are the pairwise non-isomorphic representations of G. Yeah, sorry. Okay, because as we saw, this is a trace, so this gives you the dimension. And in particular, the number of non-isomorphic irreducible representations. And in particular, of course, we have a sum, which is a finite number, so the number of pairwise non-isomorphic irreducible representation is finite, okay? Because, I mean, otherwise, this sum would be infinite, of course, because each term is at least one, okay? Since this equals G, okay, in particular, there are only finitely many. Pairwise not isomorphic irreducible representations of G, which is equivalent to saying that there are only finitely many irreducible characters. Distinct, say. But this is implicit, of course, when you say characters. And you see, once more, the advantage of irreducible characters, because you can have many representations which are not exactly the same, but they are isomorphic. And when you come to characters, all isomorphic representation gives you the same character. So to say non-isomorphic for representation gives you distinct for character. And you don't usually write distinct, because if you ask how many numbers in 1, 2, 3 are, when you say 3 numbers, you don't say 3 distinct numbers, okay? So this is important. We found that given a group, there is only a finite number of, say, irreducible characters or pairwise non-isomorphic irreducible representations. And soon we will see how many of these exactly there are. You will see that these numbers, the number of, say, of irreducible characters, is related to a certain property of the group. Okay, but we'll see that in a short while. There is an important consequence from this identity, because you see, consider the vector space of functions from G to C. Okay, so it's what you could denote as C to the G, the function from G to C, and of course it's a vector space by the usual if you have two functions, say f1, f2, and what's their linear combination, simply you do it by their values, okay? Where, say, f1, f2 are two elements of this function from G to C, and the lambda I are complex numbers. So it's a vector space, okay? And of course, it has dimension order of G, okay? Because the basis is provided by the delta function. Like I mean, after all, it's the same. I mean, you can say that this is just the group algebra. The group algebra was defined as this set, this vector space, plus the convolution product. And of course, the basis for this is the order of G. Is the dimension the order of G. But now recall that if rho 1, rho, well, whatever, T, are the pairwise irreducible, pairwise non-isomorphic, irreducible representations, well, then of course, the rho I jk, so this is the jk component of rho I, are functions from G to the complex numbers, okay? Because we are just locating within this matrix rho I of G, the element JK, okay? And we saw that they are orthogonal. Not exactly orthonormal, because if you, I mean, it's a theorem that came before the orthogonal relations in G. And if they are orthogonal, then they are independent. If there are any problems with this, with linear algebra, of course, just let me know in time. But how many of these functions we have? And there are, how many functions of this? Well, okay, suppose the rho I goes from G to GLVI. Of course, there are some from I going from 1 to T. Well, you have dim V squared of these functions for each I, okay? Because if Vi has dimension dim Vi, these are the components. So, I mean, say if the dimension of Vi is n, then you have n squared functions of like this. So if you sum over all the irreducible representations, you get this. But look, this equals this. This is just what we proved. Let's go back and check. This is this fact here, that the order of G equals this sum here. So what we have here, we have a space, the vector space of dimension of the order of G. And then we have a set of elements of this space, which are orthogonal and then independent. And look, the number of this function is exactly the number as the dimensional vector space. So you have an independent set of vectors in a vector space, okay, whose dimension is the same as the vector space. So they are equal, okay? So what we found this important corollary. Well, let's go back to black. The functions rho I, JK are a basis of the vector space C to the G. Okay, this symbol is of course something you know well. You've been known for a long time. This is space of function from G to C are a basis of this vector space. Okay, so you see that. I mean, if you consider this vector space, the space of function from G to C, this has nothing to do with linear representations. It's just a space of functions. But you see that the components. Oh yes, I have to be precise. The components of the irreducible representations form a basis of this. So these functions occur in sense naturally for where rho I ranges over the irreducible representations, pairwise non-isomorphic representations of G. So they are quite natural. There is one of the seminars that considers what happens is when you extend this theory from a finite group to a compact group, like the circle group, okay, the group of complex numbers of modulus 1. And you get a similar result, that these functions are dense, span a space that is dense in the space of all functions, continuous functions. I mean, you need topology and the like, but this is generalization. But once more, this suggests that representations are a natural things to consider when you study a group, because as I said, if you consider this space, I could have defined the space of function from G to C just before starting the course. And this is something that has nothing to do with representation, apparently. But then you see the representation provides the basis from here. And so they are an object you have to consider, no doubt. And now let's see an important result that is in a sense an analog of this for characters. And this is a subtle argument, so we'll do it with care, okay? So let V1 Vt, no, okay, just a second. Let rho I, GLVI, be the pairwise non-isomorphic irreducible representations of G, okay? So, yes, all the representation. Well, this is not very well formulated. I'm picking one for each isomorphism type, okay? So these are all the representations, except that I don't write, that I write each irreducible representation only one, okay, of G, okay. And so we can form the direct sum rho 1 plus rho 2 plus rho t, okay, if they go from 1 to t, okay? Let's repeat this with great care because it's important. So what's this direct sum? The direct sum is again a representation, okay? It's a representation of G. And this takes, so it's G from, it's from G to GL of what? Of the direct sum of the underlying vector spaces, okay? So let's recall here that rho I goes to G to GLVI, okay? And what does it mean? That you take an element G here and you send it to what? To a blockwise matrix, where here you have the block rho 1 of G, here you have the block rho 2 of G, and so on. And here you have the block rho 2 of G. And everywhere else you have zeros, okay? So that's a direct sum of representations. In terms of matrices, it's simply extremely simple, okay? Blocks. Great. So it's in this GL of V, but it's quite natural to see that this is really isomorphic to, say, the direct product of the GL of the GLs, okay? Because of course discommute, okay? So if you look at the diagonal, how do two matrices? Well, let's see it clearly. Why am I writing this isomorphism? Because consider two matrices like this, okay? So this one and let me see whether I want to copy it or not. Well, no, I won't copy it. What happens when you multiply two matrices like this? So I have, well, it's written particularly horribly, so I'll rewrite it. So this is one of the matrices. I'm not writing the zeros and the blocks, and you multiply it with this. With the same matrix for H. And then, I mean, given that that blockwise matrices multiply like ordinary matrices, what you get is rho 1 of G, rho 1 of H, rho 2 of G, rho 2 of H, and so on. And of course, since each of these is a morphism, is a representation, you get rho 1 GH, exactly, and rho T GH. So you see why it's a direct product, because how do you see this as tuples, and how do you multiply to p tuples? You see it here, element by element, okay? Okay, the first component of the product is the product of the first components. The second component is the product of the second components, and so on. Okay, so that's why you have this direct product, because they work as tube tuples, because it goes to T. Okay, good. But of course, then, so you have this map G, which goes to GLV1, direct product GLVT. And remember, let's go back for a second. This is absolutely elementary, because I'm simply telling you that the element G goes into these block-wide matrices. And these matrices behave with respect to product like a direct product, a product of T tuples, in which you do operation by components. That's exactly the direct product. Good. And of course, this, I mean, GLVI, of course, is containing NVI, which is simply, these are the matrices over VI, the linear, and these are the invertible matrices, okay? Okay, so this is contained in let me see how I want to write this. Well, it's a direct sum, but it's the same. Let's write the direct product. It's well, this is just inclusion, okay? Simply, you have a tuples of invertible matrices. Of course, this is a tuple of matrices, okay? An invertible matrix is just a matrix which is also invertible. So these are morphisms of groups. This is not a group, this is a ring, okay? So what do you get if you compose, and this is the identity. What do you get when you compose this? We just discussed this, the composition, okay? This is a morphism of monoids. Because of course, this being the identity respects anything it can, in particular the product, because in a ring you have a sum, but there's no sum between invertible matrices, of course. I mean, the sum of two invertible matrices need not be an invertible matrix. Say, take the identity matrix and minus the identity matrix, its sum is 0, so it's not invertible. But this is a morphism group, so it respects the product, and this being the identity, of course, it respects the product. So this is a morphism of monoids. And here we find ourselves again with an important property. So you have a group here. Well, let's write it in red. So, okay. And this is a ring. In fact, I could have written it as a direct sum, but I wanted to use the same symbol that I've used this. In rings, it comes to me to write this as a direct sum, but it's a ring by components. That means the operations are by components. Like, I mean, in the first course on algebra, in the Chinese remainder theorem, which we have to the direct sum of the direct product of z over nz and z over nz. I mean, ring by component. And this is a morphism of monoids, okay? Monoids, actually, the accent being on the first syllable, where this is unreadable, even by my standards. Okay, so this is a morphism of monoids. And now we have the extremely important universal property of the group algebra. Because G goes to C of G, the group algebra. I mean, this an algebra whose bases are the element of G, and the product of the basis element here is exactly the element of G. And this tells you that there is this determines uniquely a morphism of algebras. And remember that the algebras means vector space plus ring, okay? Well, more or less, I mean, this is explained in the notes, and if you need, I can talk about this. This is a universal property of the group algebra, because you have a ring, actually an algebra over C. I mean, if you're not familiar with algebra, it's a ring, but of course, take this. This is the ring of matrices, of course, it's also a vector space with respect to multiplication by scalars and so on, besides the ring. So if you have a morpheme from monoid from G to this, then this extends to a morpheme from the group algebra to this, okay? And what does it do? Let's see this clearly, very clearly. Okay, so let's start to see what this does. What's this? This is simply, I'm exploring first the horizontal line, okay? This is the map that sends G, okay, to a tuple, which is rho 1 of G, rho 2 of G, rho T of G, okay? This is exactly what we have seen here, right? Okay? So these are the matrices acting on V1, V2, Vt, okay? Okay, so, and this is from G to GLV1. Oh, well, I have to move this from somewhere else, times GLVT. Okay, good. And what happens when you consider, well, okay, but let me change this, because this is correct, of course, but we already saw that we can extend this to end, okay? Both are correct, okay? But I want it to be with end. So if I write GLVI, I stress the fact that these are invertible matrices. If I write simply end, I sort of forget that they are invertible matrices. After all, an invertible matrix is a matrix. It's a matrix, except that it's also invertible. So you have this G to the direct product on the endomorphism or direct sum. We send G to this. Now, what happens when I move to C of G? Well, this is how this universal property works. You have something defined on G, and you want to define it on the elements of the group algebra. And so I want to see what happens when I consider the elements of a group algebra. So this time here you have such an element, a linear combination of the elements of G with complex coefficients. And the idea is simply that you extend this by linearity. That is, so the image of this will be the linear combinations with the same coefficient AG of the images of the G. So this will send. Okay, so the idea is that you have a morphism of monoids here, okay? And here you have a morphism of algebras. And how do you go from this to this? By extending by linearity. That is, you know what this maps does on G, on the basis of the group algebra, and you simply, what's the value of this on this linear combination? And you see, is the linear combination of the values of this function on G, okay? So that's what it does. Yes. And of course, this is an endomorphism of V1 because there is a linear combination of matrices. Note that the rho 1 of G, for instance, are invertible matrices. If you do a linear combination, of course, as we remarked earlier, you need not find, again, an invertible matrix, but still it would be a matrix. You see, we are in end V1, which means ring of matrices, okay? Good. Now let's, well, okay, there's something more to say, but I'll say it in a second. Now consider the dimension of these two algebras. So these are algebras, which means a ring, okay, forget about this for a moment, and the vector space. okay? So we know that the dimension of C of G is simply the order of G, because C of G is the space of a function from G to C, and it has a basis, the element of G. So if the elements of G are a basis, then its dimension is, of course, the order of G. What's the dimension of this? This is a direct sum. Well, it's simply so remember, we are talking here of matrices put diagonally, okay, with zeros here. So here the matrix over V1 over matrix over V2 and so on. And so the dimension of all of this is the sum of the dimension of this. Okay, because of course you look at how many linear independent elements you have. Okay, and these are matrices over V1, so the dimension is this. But look, we just proved that these two numbers are equal. It was a consequence of these character things, okay? So you have a morphism of algebras from two algebras, which as vector spaces have the same dimension. If I prove that this morphism is injective, then just by looking at the vector space part, it will be also surjective, and then it will mean that it's an isomorphism of algebras. Okay, so let's sum this up. So CDG to say and V1 times and VT is a morphism of algebras between, so algebras, and repeat, algebras means vector spaces plus rings. Well, this is a shortcut, then there's slightly more, but they are both, you can see them as vector spaces on rings, and plus there is a relation between the two structures. It's a morphism of algebras between, and the two vector spaces. So since an algebra is both a vector space and a ring, if you forget conveniently about the ring structure for a second, you get just a vector space. So the two vector spaces have the same dimension. Okay? So if we prove that it's injective by elementary things of linear algebra, first year linear algebra. So if we prove that the map is injective, it will be also surjective. And then an isomorphism of algebra. Let's pause a bit to the, well, I will have to prove this, and it won't be difficult, but it's a chance to clarify some of the involved concepts. This is, in a sense, striking, because you take any group G, okay, and you build this group algebra. So the group algebra is formed by the linear combinations of element of G, where you multiply the element of G as they multiply in G, and then you extend this by linearity, okay? So you may think this depends very much on the group, of course, because it's built from the group. But then this theorem is telling you that this is a direct sum of matrix rings. And of course, when you consider matrix, because these are matrix rings, in a sense, the matrix rings have nothing to do with the group. For instance, what we'll find is that if G is an abelian group of order n, then all these vector spaces will have dimension 1. And so this will mean that if you take any two abelian group of the same order, n, then all these algebras are isomorphic, okay? So they are exactly the same because they will be the sum of, they will just be, sum of matrix algebra of dimension 1. Well, I'll be more precise later. So in a sense, we see that the structure of the group algebra appears not to depend so strongly on the order of G. It just depends on these numbers, because after all, this is matrix rings, okay? So if you know matrix rings, you also know about the group algebra of any group, okay? But I mean, I'll be more precise when we do that. Okay, so I have to prove that the map is injective. This is not horribly complicated, but it gives me a chance to repeat an important concept. Yes. Remember that there are two things that are equivalent. Remember that we started this course by recalling that you can define the actions of a group on a set in two ways. Axiomatically, okay, a certain map from omega times G to omega, or as a morphism from G to the permutation groups or group on the set omega. So there are two equivalent ways. And the same holds true for representations, okay? Recall that there are two equivalent concepts. Okay, recall that if rho from G to GLV is a representation, this time this is an arbitrary representation, not the regular representation, is any representation, then we can play the game that we played here, because let's play this game. So we have this, and of course this is contained in end V. We can consider this inclusion to be a map, of course, the inclusion map. And then we saw that you get a morphism of algebras here. Okay, this is just what we saw earlier. So if you have a representation, you have a morphism of monoids from G to NV, and then this yields by the universal property of group algebra, morphism of algebras. And the morphism of algebras, I have to go to the next page. And a morphism of algebras from CG to NV, okay? Very much of the model on what you can do on vector spaces is nothing else, is the same thing as a structure of a CG module, right CG module on NV, on V, okay? Because the structure of, in general, if you have a ring on an algebra R, the structure of a module, of R module on V, is exactly provided by a morphism of rings or algebras from the ring or the algebra R to the endomorphism of V, okay? This is a compact way to describe the axioms of a module, okay? It can also be used, as I recalled, to define compactly vector spaces. I mean, you have an abelian group V, you take a field F, and if you go and take a morphism of unitary rings from F to the endomorphism ring of V, you get exactly a structure vector. It's the same as declaring a vector space, a structure of vector space on V, okay? So this is the same thing. A morphism means a structure of a CG module. And what does it mean? So a structure of a CG module is equivalent, in a sense, to the first definition of actions. So it's a map from V to CG on V, which satisfies certain properties. I mean, it's just like multiplication by scalars, okay? When F is a field, the vector space means a map. So let's write it here. If you add vector spaces, it will be a map that take V lambda to V lambda, multiplication by scalars, okay? And here, it's formally the same thing. But how do you get this from your original map raw? Well, this is quite simple. You have a vector here, you have a G here, and then you send it to something that you write like this, okay? Well, of course, the sum is over G. So think of this as multiplication by scalar. No, well, I want it in red. By the scalar, okay? So exactly as in the vector space case. And what's this? Well, you started from raw, and you remember what we did here. You send an element of the group algebra to such a thing, okay? So it's exactly the same thing here, which means that V G means sum. Well, okay, just a second. Okay, so we know that each G acts on V via rho of G. And then you use this to define an action of CG on V. And so you have such an element. How does it act on V? As a linear combination with the same coefficients of what rho G does to V. Okay, so you use rho to define an action of the group algebra on V, okay? Note that on the right, we have explicitly rho, okay? Whereas on the left, we don't have explicitly rho. So let's say, if you have a certain rho, this determines a structure of a CG module, okay? But of course, if you have different rhos, let's write it here, yield different CG module structures. So in this situation here I have written this way, but I could have written the action, okay, in this way. Sorry. So okay, so the point is, we had these morphisms from CG to this direct sum of the product is the same. Okay, and I want to rewrite it like this. So what's multiplication of scalars? This works like this. You have an element. When you have an element of the group algebra, so a linear combination with coefficients AG of the elements G of G, this is sent to a product of endomorphisms, so something that sends V1, Vt to something, okay? These are maps. And what's this map? Is the map that sends V1 to Vt. Let's first start it, write it as I wrote it earlier, to the linear combination AG V1 rho 1 of G and so on, okay? This is just a repeat of what I wrote earlier. Let me come back in a second so you can, right? It's just what we wrote here, okay? That an element of the group algebra goes to which endomorphisms? To this endomorphism, okay? So if we apply it to a vector V1, Vt, it will be V1 to which apply this one, V2 to which apply this one, and so on, okay? But the point is, if we regard it as say V1 plus Vt as a CG module, we write this simply as, I mean, this morphism tells you how this element acts as a scalar, say, when it multiplies this. So this multiplied by this, so this is multiplication by scalar. Okay, I write it simply as V1 times AGG, V2 sum AGG, and so on. Where, of course, but of course, this means this, and say this means this, and so on. Okay, so here I'm not writing the row, but of course, since V1 is in the vector space V1, what does it mean that these elements operate in V1? It does it via row 1. So V2 is an element in the vector space V2. So what does it mean that these elements act on this? It acts via row 2 and so on. I mean, the fact that we are not writing the row 1, row 2 is a simplification. But after all, think of several vector spaces, say a vector space of n tuples, for instance, or a vector space of matrices, say with complex coefficients, or a vector space of functions. We always write the multiplication by a scalar as a multiplication by a scalar, lambda times something. Well, here I write the lambda on the right, but it's the same. Lambda times something. We don't use a different symbol for lambda acting on an n tuples, lambda acting on a matrix, or lambda acting on a function. And here I'm doing the same. These spaces V1, Vt can be different, but when I write multiplication oriented V1 of the vector space V1 by a scalar, I mean exactly how this scalar acts on this particular space, which is like this, okay? When I write how the scalar acts on V2, I mean, as it acts on V2, that is like this. But I don't use different notations. And this makes things a bit simpler, okay? So this is implicit. I mean, this is V1, so it will be via row 1. But again, think of the fact that we write scalar multiplication when we talk of vector space all the same way, in the same way, no matter which vector space we have. And this is, we are doing the same here, okay? Okay, so my goal is to show that this map, okay, let's see this map. So my goal, show that the map from CG to n V1 times nVt, which sends such an element. This is understood to be a sum over G to the map, which send V1 Vt. Okay, this is an element of the direct sum of this to V1 sum Ag of G, V2 sum Ag of G, and so on. Okay, where we have understood that this means via row 1, via row 2, and so on. This map is injective. Okay, we want to show this, and then we'll have an isomorphism of algebras and some consequences. Since this is a morphism, this map is actually a morphism of algebras, so in particular of rings. So in this case, showing that something injective, as you know, it's particularly simple. We will show that the kernel of this map is 0. Okay, because of course, when you have a morphism of rings, say, it's enough to prove that the kernel of this map is 0. We are nearly there, but we're running out of time. So I'll stop here and we'll continue on Monday. Let me tell you something that you have already noticed. This has been a rather dense lecture. Some of the results I've gone through may appear to be relatively straightforward, but the idea of character is a rather subtle idea of Frobenius, and as you saw, we obtained some quite strikingly deep results. So this lecture, you have to try and get familiar with this lecture until Monday, because we will build on it. I mean, so it's appropriate that it comes on a Tuesday, so you have nearly 1 week to think about it. Okay, that's it for today.